All right, welcome. Today, we're going to go on a journey right to the heart of, well, everything. We're going to break down the world around us, the screen you're looking at, the air you're breathing, even you, and figure out what it's all really made of. So let's jump right in. So, just for a second, take a look around you. That screen, the air you just took in, maybe that cup of coffee. What is all that stuff really? I mean, it might look solid or liquid, or maybe it's totally invisible, but deep down at its very core, it's all part of this one big, incredible family. Okay, so here's the game plan. First up, we'll tackle the big question, what even is matter? Then, we're going to peek into the secret life of its tiny, tiny particles. After that, we'll get into the stuff we all know, solids, liquids, and gases, and see how they can transform. And to finish up, we'll go beyond those and look at some states of matter that are, well, they're pretty out there. All right, let's get into it. Part 1. Look, before we can get into all the weird and wonderful ways that matter behaves, we've got to have a solid definition. We need to know what we're actually talking about. And you know what? The definition is actually super simple, but it's also kind of profound. Basically, if something takes up space and has mass, it's matter. Simple as that. Now that includes all the obvious stuff, right? Like a chair or a glass of water. But it also counts for things we can't even see, like the air filling up the room. It all counts. And this is the big idea right here. This is the most important thing to get. All matter, I'm talking from a solid rock to the air you can't see, it's all built from the exact same thing. These incredibly tiny little particles. Think of them like the universal Lego bricks of our reality. Seriously, if you can get a handle on them, you can understand pretty much everything else. Okay, so these particles, they aren't just sitting there like boring old building blocks. Nope, they follow a very specific set of rules, almost like they have a secret life of their own. And that secret life is what determines how all matter behaves. So let's pull back the curtain and see what those secrets are. Here they are, the 4 big secrets. First, these particles are just ridiculously small. Second, they aren't packed together perfectly. There are always little spaces between them. Third, and this one's huge, they are never, ever still. They're constantly moving, constantly vibrating. And fourth, there's a force of attraction that's always pulling them toward each other. You gotta remember these 4 rules, because pretty much every single property of matter comes from them. So let's put these rules to the test. Let's see them in action. Picture this, the smell of hot, sizzling food. You know that amazing smell? It can travel all the way across the house. But what about, say, a cold sandwich? You pretty much have to stick your nose right up to it to smell anything. So what gives? Why is that? Well, the answer is all in rule number 3, that constant movement. It really all comes down to energy. See, the particles carrying that smell are always moving, always mixing with the air. That's a process called diffusion. Now, when you heat up food, you're giving those particles a massive jolt of energy, kinetic energy. They start zipping around like crazy, moving way faster and spreading out much farther. And that's what carries that amazing smell right to you. The particles from the cold food, well, they're just moving a whole lot slower. Okay, how about another one? Think about this. Anyone who's ever done a belly flop knows that water can feel, well, pretty solid. So how on earth can a diver just slice right through it so cleanly? This little puzzle is going to show us another one of those particle secrets. This one comes right back to rule number 2. There are spaces between them. That's right. Even in a liquid like water, the particles aren't jammed together with no room to spare. There are these tiny little gaps. So the diver is literally just pushing those particles aside and slipping through the spaces. You obviously couldn't do that with, say, a block of wood, where all the particles are locked together super tight. So let's recap. We've got these rules, right? The particles move, they've got spaces between them, and they attract each other. It's really the combination of these 3 things, how much they move versus how much they attract each other, that gives us the 3 classic states of matter we all learned about in school. And this table here, it really connects all the dots. Take a look. In a solid, that attraction between particles is super strong. It locks them in place, giving them a fixed shape and volume. In a liquid, the particles have a bit more energy, so they can slide past each other. That's why liquids can flow and take the shape of whatever you pour them in, even though their volume stays the same. And then you've got gases. Their particles have so much energy that the attraction force is almost nothing. They just zip around freely, expanding to fill any container you put them in. So there we have it, our 3 main states. But here's the cool part. They are not set in stone, not at all. Matter is changing all the time, and these transformations are seriously some of the most fascinating things you can watch happen. And this right here is the cycle of matter in action. It's beautiful. If you add energy, usually heat, you can melt a solid into a liquid, or you can boil a liquid into a gas. And if you take that heat away, by cooling things down, you just reverse the whole process. You can condense a gas back into a liquid, or freeze a liquid back into a solid. It's a total two-way street, and the one thing controlling the traffic is energy. But sometimes matter likes to break the rules and skip a step entirely. For example, think about those old-fashioned naphthalene balls or mothballs. You put them in a closet as a solid, and over time, they just disappear, right? They never melt into a little puddle. That's because they're turning directly from a solid straight into a gas. And that special jump has a name: sublimation. Okay, here's a really practical one, and I bet a lot of you have done this before. You've got some hot tea and you want to cool it down fast. What do? You pour it into a saucer. But why does that actually work? What's the science behind that simple little trick? The secret here is all about surface area. See, evaporation, that's the process of a liquid turning into a gas, it only happens on the surface. So when you pour your tea into a wide saucer, you are massively increasing the amount of surface that's exposed to the air. More surface area equals a much faster rate of evaporation. And because evaporation actually cools things down, your tea is ready to drink in like no time at all. So, solids, liquids, gases, these are the states we deal with every single day. They're our home turf. But, and this is a big but, they are not the end of the story, not even close. The universe has cooked up some way more extreme, way more bizarre states of matter out there. For starters, let's look at the super hot state, plasma. If you take a gas and just keep heating it to incredibly high temperatures, you get plasma. It's this super energized soup where atoms get literally ripped apart into electrons and ions. Now, it might sound really exotic, but get this. It's actually the most common state of matter in the whole universe. It's the stuff our sun is made of. It's what every single star in the night sky is made of. And now let's swing to the complete other end of the thermometer. Super, super cold. This is where we find the fifth state, something called a Bose-Einstein condensate. This was first predicted by Satyendranath Bose and the one and only Albert Einstein. To make it, you have to cool a gas down to temperatures that are just tiny fractions of a degree above absolute zero. I mean, the coldest temperature that is physically possible. And at that mind-bogglingly cold temperature, something amazing happens. The individual particles, they stop acting like individuals. They all merge together and behave like one single giant quantum atom. So just think about that for a second. We started with something as simple as a chair, and we've gone all the way to the fiery heart of a star, and then down to the absolute coldest temperatures in the entire universe. What that shows us is that the everyday stuff we see around us, it's just one tiny chapter in a much, much bigger and more incredible story. Which of course leads to the final, biggest question. What else is out there? What other strange, amazing states of matter are just waiting for us to discover them?